Hello everybody. In this lesson we'll be looking at how data is organized in a database. As you may recall from the previous lesson, An Introduction to Databases, a database is any structured set of data. Database software provides a specialized tool for maintaining this data and provides facilities to process this so that in the correct context it can become information. Before we begin, let's be clear on what we mean by data and information. Data is unprocessed, raw values. For example, a number. Data has to be organized, processed and presented in an appropriate context before it becomes information. Processing can take a number of forms. In this example, a number is divided by an amount, then multiplied by 100 to give useful information, a percentage. Changing the process doesn't change the data. We're still using the same number, but it does change the information that's generated. This isn't very useful yet. The percentage needs a context to be meaningful. This context is created by the relationships between the different elements of the data. In this case, maybe a subject and a person. Combine all of these and you have information. So what exactly are databases? Databases are tools we use for turning data into information. A database can be any structured set of data. The fact that the data is structured is important. It's a difference between a library and a pile of waste paper. It's much easier to find useful information when your data is organized. Computer databases provide facilities for managing this data. This means storing, adding, updating and accessing the data. To do this, a database needs to be able to store both the data and the relationships between the data. And to do this, databases store data in several tables with explicit relationships between the tables. Data tables can be represented as a grid containing rows and columns. A table represents a collection of data about one particular component or topic in the database. Most databases will contain several tables. A record represents one single item in the table, a row in the table. Each record contains several fields. These fields represent the individual characteristics that make up the data described by a table. Fields are sometimes referred to as columns. This structure is what allows several people to work on the same document. With regular documents, if two people work on the same document, the first person's changes will be overwritten by the second person's changes. The person who saves last will win because they save over everyone else's work. Only that person's changes will be kept. Database software is designed to enable several people to edit the data at the same time. The software does this by using record locks. As soon as you start to edit a record, the database locks that record for changes. Other people can still access the unchanged data, but can't make changes to that specific record until you commit your changes. Then everyone gains access to both the data you've changed and the ability to make their own changes to that record. Because just one record is locked, however, they could still edit any of the other records in the table while you are busy. A relational database uses several related tables to contain data, hence the name. Each table is linked to other tables using explicit relationships. These relationships provide a lot of the context that is necessary to make data meaningful. The relationships make it possible to process data that draws on several tables by combining the data from the tables using these explicit relationships. Database design largely involves structuring these tables and relationships. Optimizing databases to be efficient and give the results people need can be a complex process. This job falls to database administrators, DBAs, who design and build databases. And database administration is a specialized job and can be a very lucrative profession if one is good at it. There are three basic types of relationship you can have between sets of data. One-to-one relationships mean the values on each side of the relationship can only apply to the value on the other side of the relationship. For example, a person and an ID number. Each person will have a unique identity number, and each identity number can only apply to one person. One-to-many relationships are by far the most common relationship used in databases. In one-to-many relationships, one element on one side of the relationship can be related to several entities on the other side of the relationship. For example, a classroom can simultaneously contain several students, but a student can't simultaneously be in several classrooms. Many-to-many relationships are often represented using intermediary tables. In many-to-many relationships, entities on both sides of the relationship can link to multiple items on the other side. A subject can be taken by several students, and students can take several subjects. Database design involves planning these relationships to provide the most efficient access to your information possible. This means avoiding redundant data, where the same data is entered multiple times in a database, and minimizing internal dependencies that could create errors or anomalies, such as, for example, places where a field references data that does not exist, either because the target has been deleted or because it has been omitted. To create these relationships, it's important to be able to identify a particular record in a table. This means you need at least one value that is totally unique to only that record. After all, if nothing is unique, how can you tell your records apart? This unique value is called the primary key. Each table should have a primary key. Then other tables can have a field that refers to that primary key. This creates a link that can be used to associate any record in the first table with any number of records in the other tables. This field in the other tables is called the foreign key, because it refers to the primary key from a foreign table. With data so important, it follows that a big part of database design involves structuring tables and relationships in ways that minimize errors of the sort that can lead to corrupted data. Errors that lead to corrupt data are known as anomalies. There are three basic types of anomaly. Insert anomalies, which occur when the design of a database prevents a user from entering or inserting data when they need to. For example, when entering data in one table requires a reference to data in a second table, but this data does not exist. Delete anomalies occur when deleting one piece of data results in other unrelated data being deleted. Delete anomalies most obviously occur when unrelated data is stored in the same database table, but this is not the only way that this can happen. Lastly, update anomalies occur when a change to a specific piece of data requires changes in more than one record in a table or a set of tables. Update anomalies often occur when data is duplicated in some way. Preventing anomalies is part of ensuring the integrity of your data. Data is always at risk, both from physical dangers such as fire and theft of hardware, but also from less tangible dangers such as data theft and corruption due to bad data capture practices. Data integrity can be summarized as making sure your data is safe. Protecting data is also extremely important and has both a physical aspect and a software aspect. Physical integrity involves making sure that the physical storage of the data is protected and that hardware or software failures will not lead to the loss or corruption of the data. Measures one can take include security of the building housing the database, backups, uninterruptible power sources, UPSs, and generators. It also involves making sure that the database structure and relationships defined in a database give a clear and logical representation of the data. Logical integrity ensures that the database structure provides a good description of the data as it applies to a particular context in which the data is being used. Referential integrity is one method of ensuring logical integrity. This ensures that the one-to-many relationships defined by primary and foreign keys remain consistent. In other words, deleting a record from one table should not affect the data in the other tables. And this also means in making sure that no references are left hanging because they have references to targets that no longer exist. The process of designing a database and optimizing it to ensure logical integrity of the data and prevent anomalies is known as normalization. Normalization is a process for organizing a database into tables and fields in a way that accurately reflects the data that needs to be contained in the database, while ensuring that there is no duplication of data in the database. Normalization follows a set of rules in which the data is restructured to meet specific requirements, also known as the normal forms. These are usually abbreviated, so 1NF is used for the first normal form. Here you need to make sure that data is represented in rows and have a primary key, with the minimum number of columns needed to contain the data and no duplicate values. 2NF is used for the second normal form. To the requirements of 1NF, you add making sure that only data related to that specific primary key is contained in the table. 3NF, the third normal form, is where you make sure that no columns depend on each other. That is, no change of data in one column requires changing data in another column. The databases you use in school only contain one or two tables, so normalization is not an issue, and the process involved is not part of your syllabus. But normalization remains an extremely important part of the initial design of any reasonably sized database. That's it. I hope you enjoyed this overview. Please remember, good data is valuable. As Tim O'Reilly, founder of O'Reilly Media and one of the people who helped popularize the term open source, puts it, we're entering a new world in which data may be more important than software. Thanks for watching. I'll see you next time. Bye for now.